physics. Well, good morning, everyone. We'll start where we left off yesterday for the second lecture. So after reminding you the last things we discussed yesterday, which is basically the basics of gluon radiation in coagulable plasma, we will use this knowledge to try to basically derive a simple formula for the nuclear modification factor, just to show you how we can start with this elementary process, which is the medium-induced radiation, go all the way to an observable and compute and understand the impact of such an elementary process of energy loss in the medium on an actual observable, which is a jet spectrum. So I'll try to do a simple calculation to show you how this works. Then in this second part, I'll introduce some of the basic formalism, field theoretical formalism behind these calculations. So of course, you can do parametric estimate to understand the physics. So we don't need to go through a very detailed calculation. But I wanted to show you, for those who want to know what's under the hood, really the technology that's used to do these kind of calculations, which is based upon light perturbation theory, which I guess you saw probably with Yuri earlier this week. Then I'll show how using this formalism we can calculate again the medium-induced gluon spectrum, and I will conclude by revisiting the factorization theorem in heavy ion conditions. Okay, so let's start. So this is again what we saw yesterday. The medium-induced gluon radiation, which is triggered by coherent multiple scatterings during the formation time, which is typically much smaller than the length of the medium. This formation time scales like the square root of the frequency of the gluon. So the softer the gluon, the faster it is produced, right? So this blob gets smaller and smaller the softer the gluon, right? And you can view it as really, as compared to the size of the system, as quasi-instantaneous radiation for soft gluons. So soft gluons are radiated in quasi-instantaneous manner, and this can happen with concentrate anywhere along the medium, right? So you can imagine many of these processes happening in a row. So again, we have maximum frequency here that tells you which corresponds to formation times of the order of the length of the medium. So this is where the all of the medium acts as a single effective scattering center. So okay, think about it. So you have a gluon that has a formation time which is as large as the medium and sees the medium as a single scattering center. So this means that the intensity of this radiation should be strongly suppressed because just a single scattering is acting on this radiation. This is called the LPM effect. And this is a spectrum we saw yesterday. That was the last slide, right? So as I said, you can view increasing this frequency here, omega. As you increase omega, you are increasing the formation time, right? Square root of omega, increasing formation time. Increasing formation time meaning you are decreasing the effective number of scattering centers and hence decreasing the spectrum. So as you can see, the spectrum initially is flat. This is where basically the radiation is triggered by incoherent scattering center. Only one scattering center is responsible. So then you have to multiply by the number of scattering centers, right? If you have n scattering centers, you would have n times the radiation of a single scattering center, and this gives you this called the Bethe-Heitler regime, right? This is a very soft regime. The formation time is of the order of the mean free path here. And as you increase the frequency, you start the gluons start feeling more and more scattering centers again, and then this will lead to this suppression, which goes like 1/√ square root of omega for the radiative spectrum. When you hit the maximum frequency, omega c, which means the formation time is of the order of system size, there are no more scattering centers, no more medium, then you reach the maximum possible suppression of the spectrum, and then the spectrum drops even faster and goes like 1/√ omega. So this regime, the LPM regime in between here, where the formation time is between the mean free path and the length of the medium, as I said, you have soft gluon radiation triggered by multiple scatterings. In this regime, the very hard regime, when the formation time is much larger than the medium, this is triggered by single, very hard scattering. That's how you can produce this high frequency, right? This is not very interesting as we will see shortly. We can ask the question, which regime is important for energy loss? Which one will really lead to the strongest energy loss? Well, naively, you would expect this regime to be important, right? So, well, that's the largest frequency. So, in principle, but this is suppressed, right? The spectrum is suppressed. So there will be somehow a competition between the suppression of the spectrum and the frequency here on the level of the energy loss observable. Okay, so we want to use this to calculate the actual energy loss of a single hard particle, right? So let's think of a jet as a single fast particle, not the collection of particles, just as the leading order calculation. So a general formula we can write immediately, right? So the spectrum, d sigma over dpt for a jet produced in the medium should be written as or factorized as the spectrum of that jet produced in vacuum. Why we are allowed to do that? Well, simply because the formation, as I said yesterday, the formation of the jet is instantaneous. It doesn't know about the existence of the medium. So the cross section for that jet before even interacting should be the same as in proton-proton collisions. That's what I refer to as the vacuum cross section. And they say, well, I have a jet which has a certain energy, not PT here, but E, right? I start with an energy E. And the question is that there's a probability for that jet with energy E to lose an amount epsilon of energy while going through the medium. What we measure is the PT. So the energy, the initial energy is equal to PT plus epsilon. So you lose, E loses E epsilon, we measure PT, right? Okay. So typically the spectrum drops as a power law, and this is an important information. So it goes like 1 over pt to the power n, and n is large. So you have a steeply falling spectrum. And this is important because this will affect what range of frequencies will, in fact, impact the observable. All right. So now we want to compute this probability distribution. So we know we know how to compute the leading order medium-induced gluon spectrum, which is given by alpha s proportional to alpha s, a single radiation here. And as I said, it's given by the square root of this maximum frequency, omega c over omega. Why square root omega over omega? As I said, it has to scale like L, as the protection here is occurs with constant rate along the medium, so it's proportional to the system size. Okay. And then, of course, the other time scale is formation time. So you take L divided by the formation time, that gives you square root of omega c over. That's the radiation length, but that's for the radiation intensity. And this happens with constant rate along the medium. So many radiation could happen somehow sequentially, right? So we need to account for all of the radiations that happen quasi-instantaneously, right? To account for all of the energy loss. So here in this depiction, we have 3 gluon radiation. It could be any number, right? And this happened quasi-instantaneously. So because these are completely uncorrelated events, okay, because of the short formation time, then the distribution of energy loss should follow Poisson distribution, all right? So the Poisson distribution here is given by simply, again, the exponential of the mean number of radiated gluons, which is just the integral of this spectrum, a multiplication of all of the spectra here of the all of the radiated gluons. So you multiply all of the spectra, and then of course you need to measure the energy loss, which is epsilon, which is just the sum of frequencies of all of the radiated. And then because you can't distinguish between the gluons, you have to multiply by this symmetry factor 1 over factor n, right? A way of constructing this distribution, another way, is to order these radiations in time, right? You could imagine that this first radiation happens at a certain time t1, and then the second one at t2. And typically, you would have the first, let's say, the leading order, the order alpha s would be, let me write it like this. First of all, the order, let's say the order 1 should be P0 epsilon, which is just a delta function of epsilon, right? No energy loss. That's a delta function of epsilon. Now at alpha s, we should expect this to follow just a single radiation, epsilon minus omega, and then I have to integrate over omega from 0 to infinity, right? So that would be the alpha s order. And now you can go to the next order, alpha s squared, all right? Alpha s squared, it should go like, I have two radiated gluons, two spectra for one. Hopefully you can see from here, everybody can see. And then I have a delta function. And then here at this level, I need to integrate. Let me do it again here. I need to integrate over the time from 0 to, let's say, L to T2. All right, so I need to integrate over the time, production time of the gluon all the way to T2 because it's produced before gluon 2 and then gluon 2 from 0 to L, all right? And then I integrate over omega 1, omega 2 for the spectra here, all right? But we are talking about rates now, so we need to take the differential spectrum with respect to the time, which is basically taking the derivative with respect to L there, right? And here we have epsilon minus omega 1, this omega 2, right? We're not done yet. So basically here, integrating over time, assuming this is a constant rate, with respect to time, the integral here gives you the 1 over factorial times L squared, all right? Okay, so this is the L squared that we want to resum. This comes from the product of these two spectra. Now we're not done yet.
Back.
Yeah.
The second line is a single gluon emission, right? Then why is order alpha? Should not be order G.
Order alpha because you have one gluon emission, so you have a vertex, one vertex. It's order G squared because you have G in the amplitude and G in the complex conjugate. If you do the calculation, right? So you have, let's say, if you do calculation of Feynman diagrams, you have scattering, right? This, we don't count this. This goes into Q hat, right? Then you radiate. You have a G here, and this is order G squared, which is so one in the amplitude, the other one. So alpha s is the lowest. Let's say G squared is the lowest power of G that you can get from calculations in perturbation. All right. So what I didn't tell you is that we're talking about. So we understand now how we can generate this symmetry factor, right? Something is missing here. Is the exponential, right? This exponential is there for probability conservation. This is a probability distribution. So we are counting radiation, but we are missing on virtual diagrams, right? A virtual diagram is typically a radiation, let's say this kind of, self-energy diagrams. You radiate and absorb on the side of the amplitude. So this is the kind of contributions that do not account for any, not participate or contribute to energy loss. So this is just a delta of epsilon. So in fact, I need to remove that epsilon, delta of epsilon here, to have probability conservation. So probability conservation is important. So we need that integrating the distribution, let's say, at every order in perturbation should give us, well, here it should give us 0 for n larger or equal to 1, right? So we need this. So basically the first order integration, or integrating this from 0 to infinity, this gives us 1, right? And then for any high orders, I should get 0, right? Just by probability conservation. So here you can check that it's indeed working. If I integrate over epsilon, I get 1, 1, and I get 0, right? I should do the same in here. I should include all of the diagrams that should cancel. And this is done in a systematic way through this exponential. And at the end of the day, you get the Poisson distribution. I'm just showing you how you can derive it from an actual calculation. But at the end of the day, you indeed get Poisson distribution, which is given by probability measure this random variable n 1 over n factorial some exponential N here, and then of course have right. So this is that's the distribution, right? This is basically the Poisson distribution. All right. So now we have our distribution, okay? And here we are neglecting. So the hard regime, right? So here omega must be smaller than n, right? Otherwise, this formula doesn't work. Okay, we need omega to be TF to be much smaller than n to be able to factorize like this radiation. Now, if omega is of the order of the maximum frequency, this gluon here should have a formation time which is of the order of L. So this factorization should break down. Okay, we'll have interferences between the gluons. But this is fine because this is power suppressed. I can just treat it perturbatively. I just say, well, I just compute the leading order, which is just the P1, if you wish. So just P1 at this order, the alpha S order. So this control. When omega is soft, much more than omega C, I can resum to all orders because I have a length enhancement. But when omega is over omega C, as you see it here, omega of omega C, it's over order alpha S, right? I can just treat it perturbatively, right? Okay. So now I have a Poisson distribution. I have a convolution in frequencies. And how to solve it? Well, there's an easy way of doing it, is to go into Laplace space. Going into Laplace space defined here by this transformation, and nu is the conjugate variable to epsilon, then I get an exponential. So the convolution in frequencies turns into a product. And then I just get a typical exponential here. The way you can view it, the way you can view how this convolution turns into a product is simply by, we do it here. So typically, so we have, remember, so we have this. So I define the Laplace transform, which is I integrate over epsilon exponential minus u epsilon of epsilon. All right, so I have this. Let's do it for two gluons, okay? So this is going to be minus u epsilon. And I would get 1 over, let's do for the full distribution. Okay, and here I would have a product of the spectra, right? And then the trick is to integrate. So there's an integral here over all of the frequencies, and there is a delta function epsilon minus omega 1, omega n, right? Now the trick is after integrating over now epsilon here, I can replace so epsilon in the exponential by the omega. So basically what I have, and then of course the sum of the omegas turns into a product, right? All right. So do you see the factorization? And this product now I can integrate over omega 1 in for the different spectra individually. So each spectrum right here would be associated with this. The result is in fact just a product of the integral here. Now the I is not necessary anymore. I get minus omega d over d omega to the power n 1 over n, right? So I'm missing here on other factors like the exponential. So there's an exponential, right? So this is what you get. You get just a product of the Laplace transforms of the radiative spectrums. And then this is just a representation or the Taylor extension of the exponential. I just exponentiate, and this is what I get. Again, the one term there is the term in here. The one is just related to the exponential of the mean number of gluons, and the exponential minus nu, the second term here, is what I just calculated, right? So now I have a simple and tractable formula, just an exponential. So I can just evaluate it, right? So I just plug in the spectrum, which is 1 over square root of omega, okay? and I end up having this standard integral, right? I just factor out x being just the dimensionless quantity, which is omega over omega c. I just factor out everything else, and it's just a number, pure number, right? Just square root of pi. All right. So I have square root of pi times the square root of nu, and this is what you get for the Laplace transform. So the Laplace transform is just an exponential of square root of alpha s squared, right, times the maximum frequency, omega c times, all right? So that's the result for this calculation. And then you can transform back into frequency space, doing Laplace, inverse Laplace transform, and then you get this distribution here. And you can see that the scale that governs the energy loss is no longer, it's not omega c. You can see it here, right? So the scale that governs the distribution is alpha squared omega c. So it's not the maximum frequency that governs energy loss. It's really a much softer frequency, which is suppressed by the square of the coupling constant, which is assumed to be small. So it's really, energy loss is dominated by soft gluon radiation as anticipated. All right. Now we want to, so this is what you get after plotting the distribution. So this is the distribution, the energy loss distribution, plotted as a function of this reduced variable x, which is epsilon over omega s. Omega s, again, is the actual variable we are after. It's alpha s squared omega c. This is the soft physics. Omega s would sit somewhere in here around the tail. So the peak here is around 1. This is omega s. The typical frequency is soft. And here, this is the hard tail where you have rare events. Now, there's an important observation to make here. The mean energy loss, if I were to compute the mean energy loss meaning I multiply epsilon by the probability distribution, I integrate, all right? So if I integrate over epsilon, I could do that, right? I could say, well, maybe energy loss is given by the mean. And you could say, well, let's compute maybe E loss is given by the mean energy loss, which is the integral epsilon to infinity epsilon p epsilon. I could do that. And is this an accurate description of the physics? The answer is no, because this is dominated by large frequencies over square root of epsilon, right? From 0 to, you see this is divergent, okay? So I would need to cut it off at omega c because I know the spectrum drops faster, right? So there is an omega c sitting in here, right? So there's omega c and alpha s. So there's square root omega c here. So if I integrate here, I get alpha s omega c, right? So what I'm getting here is that the mean energy loss is sensitive to the physics around the hard scale omega c, okay? While, as you can see here, it's really heavy tail. These are called heavy tail distribution, which do not admit moments. If you integrate compute moments, they diverge. But of course, we know that there is a physical cutoff there, which is omega c. So there is the region around the mean energy loss is not a good description of energy loss. Why so? Because to compute energy loss, we need to convolve our distribution with the spectrum. Remember, we had to do convolution with the spectrum. So the spectrum goes like the initial spectrum goes like 1 over pt to the power 1 over pt to the power n, right? And if you do that, you convolve with the spectrum, then the distribution gets skewed towards even softer frequencies, as you can see. So multiplying by the spectrum, you suppress the hard tail here, and then you are even more sensitive to the softer gluons. So the distribution, in fact, the frequencies of the energy loss that dominates the process here are frequencies of the order of the jet pt divided by n, as you can see it in here, right? So we'll see here how this comes about. So typically here, when x is larger than pt over n, you get a suppression, right? So this simulation here, these are the numbers I use for this calculation. All right. So let's go back to the problem of jets. We have a jet initially that produced with this spectrum, 1 over pt to the power n, and loses energies, which shifts the population that's sitting at a certain pt to lower PTs. So this is the physics of energy loss. You are shifting a certain population of jets that sit at certain PT at lower PTs. But at the fixed PT, what you would see is suppression, right? At the given PT, the effect of energy loss is suppression. This is the so-called quenching of jets. So again, we have the power spectrum, all right, in here. And I know the distribution, I've computed it, and I can compute the RAA. So the RAA is nuclear modification factor, which is just the ratio of the jet cross-section in the medium divided by the jet cross-section in the vacuum, which we know is just 1/pt to the power n. And then if I take the ratio, right, 1/pt power n will just combine with this power here, giving me 1/1 plus epsilon divided by pt to the power n, right? So at this point, I can just evaluate this, right? But there's another approximation I can make where I know n is large. So the spectrum is steeply falling. Because I have this steeply falling spectrum, in fact, this will, as I showed in the previous slide, makes energy loss sensitive to really small deviations of small values of energy loss. So typically, when n is large, energy loss is given by pt over n. So the larger the n, this spectral index, the smaller the energy loss, right? So what I can do, well, I can just use this representation of an exponential. Right? When n is very large, even though epsilon is small, right? N times epsilon could be of order 1. N times epsilon over pt could be of order 1, okay? So typically, even though epsilon is much smaller than pt, okay, I could have n times epsilon of the order pt, right? So the Taylor expansion will break down. I cannot just say, well, I'm going to expand in powers of epsilon, which leads to the mean energy loss. No, I need to account for the fact that even though n is small, n times epsilon is not small, and this is what we get. We can approximate this power law by the exponential, okay? And we are neglecting powers of epsilon times divided by pt times n. There's an n missing here. Okay, so putting everything together, well, what I forgot to mention, this trick is very useful. It comes in handy because I get the exponential, which I need to connect this to the Laplace transform, right? So remember, the representation in Laplace space was very simple, right? It was given by this exponential in Laplace space. So in fact, I didn't really need to evaluate the distribution in physical space. And just go back here now and use the fact that the distribution now is multiplied by this exponential integrated over epsilon, which is just a Laplace transform, evaluated at the frequency n over pt, well, at the Laplace variable n over pt. Right. Okay. And this is the result. This is what we get. So we're just, the RAA is roughly, to good approximation, just the Laplace transform of the energy loss distribution evaluated at this specific value n over pt. And this is what we get. We get an exponential of the minus square root of n. So we see that n plays a role in the suppression. So the larger n, the more suppressed is the spectrum, right? The more suppressed is the jet spectrum. There's an alpha squared related to the radiation, of course, omega c divided by pt. All right. Again, we see that the scale that governs suppression is really alpha squared omega c. And this is what you get. When you get the RAA, well, yes?
What was the factor of n? What was the mean?
The n?
Yeah.
Factor n here, right?
Yeah.
N is the power index of the spectrum. So the spectrum falls as 1 over pt to the power n, right? And n is typically of the order 5 to 6. So at leading order is a 2 to 2 matrix element, which is 1 over pt to the 4th, roughly. Okay.
Parallel function.
Yeah. So this is just a simple calculation. Even though we of course, this is an illustration. The actual calculation would involve, you know, taking into account the geometry and so on and so forth. But this is really the basic idea of how we do calculations in jet energy. All right, so the formalism.
Sorry, I have just a quick question. On the previous one, for that one, if you have a that you had, is the same. I'm trying to say, like you had itself is the same, but then at different PTs it affects it differently. Is that what that's still, right?
Yeah, exactly. Yes, you would have this. So the RA for a given Q hat should increase with PT. So the idea, if n is fixed, right, is the spectrum is really just a power law, right, and n is a constant number, then we should expect RA to go to tend asymptotically to 1. So if PT goes to infinity here, you see that this RAA, this exponential goes to so the argument of the exponential goes to 0, so the exponential goes to 1. So this happens slowly though, right? You see it happens slowly. It goes really slowly to 1, right? There are other the caveat here because the n is not constant. It varies with PT slowly, but it varies, right? But indeed, I mean, you should expect an increasing function of PT. All right, so I might not have time to cover everything, but at least I wanted just to give you, you know, a certain flavor of the technology that's used. So now the first thing we want to do is to define the kinematics. We have a jet, high energy jet, that goes through the plasma. And what we usually do, where we usually change variables, we use the light cone variables when we have a high energy object in high energy collisions. So we use light cone variables defined as basically x plus defined as t plus z and x minus defined t minus z, right? So the jet trajectory is, because the jet is moves close to the light cone, moving at the speed of light, then the trajectory is along this x minus equals 0. So basically t equals z, right? So this is the trajectory of the jet. The size of the jet along the x minus direction is given by 1 over p plus being the longitudinal component of the which is large, one component of the momentum of the jet, which is large. So when the jet goes through the plasma here, well, it's mostly going to see the plasma along this trajectory, which is x minus close to 0. This is the same approximation used in high energy scattering, VIS, and so on. So it's very similar, those who are familiar with this type of approximations. The other approximation is, of course, again, it's the same approximation, high energy approximation. The energy is large, much larger than any transition momentum transfer, which means that the jet stays a jet. It's not deflected at larger angles. Now the coupling. The jet couples to the plasma. How does it couple? Well, because the plasma is much softer. It's made of gluons that are much softer than the jet. The interaction is mediated by the interaction with the background field, which encodes the physics of those soft gluons. So this would be the vertex. So this is just the quark one vertex. So this the left-hand side is the interaction term in the Lagrangian, right? You would have basically psi bar a psi, right? That's like just here in momentum space, just by using the spinors, a background k u p minus k. So this is this diagram. I have a k here transfer. I have a p minus k, and I have a p, right? So at high energy, this vertex is simply proportional to p u times the gauge field. Okay, that's the equivalent approximation. So I am dropping in this approximation. I'm taking p plus to infinity. That's the limit, p plus to infinity. So I'm dropping powers of k plus over p plus, right? And this is what I get. I just get some very simple form, which is a projection of the field on the momentum for vector of the for momentum of the jet, right? And I can integrate over k plus here, and the integral over k plus gives me the evaluation of the field at x minus equals 0. This is what I mentioned before in the previous slide, that the jet basically feels only this trajectory here, x minus equals this region of the background field. Okay, so there's another important aspect which makes this physics a little bit different from the technology used in high energy scattering, say for small x physics. It's very similar, the same technology. The difference is now while in small x physics, you would assume that the target is Lorentz contracted, so the interaction is instantaneous. Here, the medium is large, right? So you can't do that. You can't just assume that the trajectory of your particles through the plasma are just straight lines. You can't just do that. Because the particle can explore the transverse space through actually propagation, quantum diffusion, which is encoded in just the standard propagator here. So we can neglect powers of k plus over p plus, but we cannot neglect certain powers of p plus, which are enhanced by the medium size, which are encoded in the phases. There are some quantum phases in the calculation which come from simply the propagators. The propagator, if you Fourier transform with respect to the x plus variable, you get a phase, quantum phase. And if x plus is large, of the size of the L, so this phase cannot be neglected. I cannot just say, well, p plus goes to infinity, let me just drop it. I cannot do that. And this phase is very important because this is the quantity that plays a role in the LPM effect that leads to this 1 over square root omega, which was simple to do. The derivation was simple, but in fact, in the way we get it from a calculation is really by keeping the phase. So I think you can see it here. If I plug numbers, pt squared over p plus, this phase, times L, or plus, so this is just a parametric estimate. Then pt, remember, pt squared was roughly q hat L through the momentum broadening, trans momentum broadening, q hat L. And when I get here, I get that the phase becomes important when k plus, which is the frequency here, k plus is the frequency, omega, is much smaller than omega c. So when omega is smaller than omega c, the phase cannot be neglected, although p plus is large, right? Feel free to ask questions if anything is not clear. All right, so now I have a background field. I know that the interaction is iconal, so there is no spin flip. So this is spin or gluon helicity is conserved along the trajectory. This is a tremendous simplification. So all of the Dirac operator for propagator, for instance, simplifies into just a projector. This is just the Dirac structure, which we can just forget about. It's just a projector, projects onto a certain good component of the spinner, and then I'm left with a scalar propagator. So my Dirac propagator, which has this kind of spinner structure, is just proportional to a scalar propagator, which is just a standard, which solves a Klein-Gordon equation. So I have a field here. This is what the propagator is doing. So I'm resumming to all orders insertions of this background field, and in between I have, of course, free propagators. All right, so what happens now is something very neat here and rather interesting. When I change space, instead of working in momentum space, fully momentum space, I work in some kind of a mixed space where I integrate over one of the over x minus. Then I turn the scalar propagator into this kind of Green's function, which obeys the Schrodinger equation. This is rather interesting. So the physics at high energy, this is known, but high energy, the physics is in fact can be described by, can be described by 2 plus 1D non-relativistic quantum mechanics, where the energy of the jet plays the role of the mass. So this is just Schrodinger equation. I have a potential here, right? This can be understood as an evolution operator. You can replace it by also the wave function here. So this is interesting. So now the problem simplifies a lot because we all know how to deal with quantum mechanics. The last ingredients to be able to compute observables. Now I know how to compute propagators. Very simple, well, very simple. At least formally, they obey Schrodinger equation. And then I need to average over the field configurations. I can compute observables as a function of a given field configuration. and then I still need to average over that. So this is also used in the context of small x physics or saturation physics by using the Mehtar-Tani model. We have a background field which we need to also average over. And then we use this Gaussian statistics, which gives you this two-point correlation function for the field, which is just a delta function in x minus y plus, and then multiplied by the elastic cross section. All right, so this is the tool that we use. Now we know how to perform averages, we know how to compute for a given configuration, and now we can compute observables. So the jet in the icon approximation for the jet, when the energy goes to infinity, can be described by so-called Wilson line, which is a path order exponential. This comes about simply because we have the propagator is simply simplifies in the limit where p plus goes to infinity. So this is the propagator, 1 over p squared. I write it like 1 over p plus p minus p perp squared. And the limit, when p plus goes to infinity, this goes to 1 over p plus p minus. And there is no dynamics in the transverse space. There is no dynamics in the transverse space. And when Fourier transform, I get Wilson line. So the Wilson line is just a product of the fields at different light times. All right. I just integrate over or the power n, right? And I exponentiate. The exponential, in fact, is just a formal way of saying that I have an ordered exponential. So the point here is to say that this Wilson line is our building block for computing energy loss. It accounts for the interaction with the plasma through the background field, but also for the radiation, because I can split the field here into a background field plus a quantum fluctuation, which describes the radiation. All right, so I'm saying that the Wilson line somehow encompasses all of this soft physics in the plasma. So now we have the tools to construct our probability distribution from field theory. So the energy loss distribution that we discussed, which we kind of derived using very simple considerations without doing any actual calculation, right? We got the right answer, by the way, without doing any calculation, but we should be able to have a more robust definition. And this can be given by this operator here, which is a correlator of the Wilson lines. One Wilson line in the amplitude and the other one in the complex conjugate. Okay, one will describe the radiation in the amplitude, the other one in the complex conjugate, and this x here is just a measure. Here the delta function is telling you that wherever x state, which is all of the particles that are radiated by the jet, I just measure the ones that account for energy loss, and this is the delta function here. Now, if I integrate over epsilon, obviously what happens is that the delta function disappears, and the sum over x here turns to 1, right? So it turns to 1, and then the Wilson lines, they just collapse, they cancel each other, and I get 1. So by definition, this is in fact unitary. So this quantity here, in fact, encodes diagrams like this. So you could radiate a gluon, then this gluon can radiate again. So this is the kind of all-order type of pictures that are included in here in this type of diagrams. So to conclude this lecture here, I have a few minutes left. Let me show you now how we can use these technologies, these building blocks. We introduced the Wilson line, we introduced the scalar propagator. That's all we need to compute, processes. The process we want to compute here again is the one that we discussed earlier, which is the medium-induced Coulomb radiation. So now, how do we go about to compute this? Well, we know that the jet, we start at a certain time for light time at 0, right? Will propagate through the medium, and then at some point, at some time, x plus radiates a gluon, and then continues along a straight line trajectory. So the trajectory of the jet is a straight line. It's a Wilson line. So all of the interaction with the medium here are implicit. there are insertions of the background field just to make the figure less busy. So it should be understood that these are not free propagators. They are really dressed by the interaction with the medium. So you radiate a gluon, and then the gluons will just propagate according to this scalar propagator, this Schrödinger type of propagators. And then you have Wilson lines here, which are responsible for this color precession. All right, now I multiply by the complex conjugate. So usually when you do the calculation, amplitude times complex conjugate, everything is done in momentum space. The way we depict it is in this fashion, right? You have the amplitude on left-hand side of the cut, and then the right-hand side, you have the complex conjugate. In this context, because we are working in this kind of mixed space where we actually measure Lightcon time, we follow the Lightcon time, it's more convenient to fold the complex conjugate on top of the amplitude, right? To evaluate them at equal time, right? So this is the complex conjugate, which is also a function of time scales here, which we fold on top of the amplitude here. And this representation, which is also reminiscent of the Schwinger-Keldysh formalism, is very powerful in terms of really computing expectation values of the background field, as you can see. So here, the first thing, well, the quark here and the amplitude and complex conjugate, they are on top of each other. The Wilson lines are on top of each other. So because the Wilson lines are on top of each other, what's going to happen is that they just collapse to one. So before the emission, there is no contribution. Nothing happens. So there's an exact cancellation of the interactions before. The same thing happened after the emission in the complex conjugate. There's a collapse. U dagger equals 1. Now, but this we understand because the radiation spectrum should not be determined by the physics of the jet. So if the jet interacts in a certain way, this should not affect the rate of radiation. The only the only regime where we should expect a contribution is between the radiation time and the amplitude and the complex conjugate. This is the interval in time where the gluon is formed.
Just a quick question, and apologies if you've said it already. This is true, like for the higher energy, higher PT. So, like for example, at RIC, at STAR, where the jets are, on a good day, maybe 20 GeV is my understanding. Does everything still apply, or I've heard that it gets a little bit more complicated with.
Yes, it gets more complicated. Well, this is again a quantitative question. What you can do is you can start with this approximation, high energy approximation, and compute corrections, power corrections. At RIC, maybe you would need to compute higher powers, 1 over ET to some power, right? Or you need a different technology,
okay,
right? So a different one, which I didn't discuss here, which we have currently. But yes, indeed, you're right. There are corrections that become more important as PT goes down.
Yeah. Okay, thank you.
Yes. And then what happens again here, the Wilson line of the quark and anti-quark between the emission and do not collapse simply because you have this solutions of the color matrices here. So in fact, this insertion here leads to a quark anti-quark combined into Wilson line in the adjoint representation, which is like a gluon. So the quark anti-quark behave like a gluon here, as you see. So all of this very complicated kind of process here, without doing much algebra or very simple algebra, I can reduce it to just a 2-point function where I have just a propagator in here times a Wilson line adjoint, right? Very simple. It doesn't look like it's simple, but it's very simple in terms of field theory here. So here I integrated over the transverse momentum of the gluon also, right? Why the further propagation of the gluon didn't matter? Because, well, if I integrate over the KT, I don't measure the broadening of the gluon, so it shouldn't really contribute to the observable. Again, so I'm measuring only the frequency. All right, so this is the object we have. Now, my spectrum will be proportional to the correlator of the Wilson line joint that describes the propagation of the quark or the jet. And then, of course, you have the scalar propagator that describes the propagation of the gluon. And this is a non-perturbative definition. I have now an operator that I need to evaluate to compute the radiative spectrums. And again, this Green's function here obeys the Schrodinger equation again, where now I have, instead of the field, I have this imaginary potential, which is related to the elastic scattering cross-section, right? And I guess you've seen something similar in the lecture small x. So this cross-section is just the 2-to-2 matrix element that is now fully transformed in transverse space. So the Fourier transform leads to this quadratic behavior, x squared times a Coulomb log, which if we neglect the log here, well, you can just write it as q hat. So the potential is some constant q hat times, and this x squared is not a coincidence, because we talked about momentum broadening, right? And we said that this was some kind of Brownian motion in this space. And Brownian motion is described by Gaussian distributions. And this is not a coincidence that we got this x squared. This x squared reflects the Gaussian nature of the Brownian Brownian motion in transverse momentum space. All right. So what we can do with the log, in general, it's difficult to solve this. What we do, we can just solve it order by order in the insertions of the field. This is the opacity expansion. Or we can just ignore the log and solve it to all orders in the so-called harmonic oscillator approximation. We can solve, in fact, by solve to all orders in the fields interaction this quantity. And this is why we were able to compute multiple soft scattering. So we can compute the spectrum to all orders in the insertions of the field, leading to this LPM suppressed spectrum. And this is the result you get numerically. So numerically, so this is, I would say this is the state-of-the-art calculation for the medium-induced spectrum using this formula, which cannot be solved exactly analytically. So the state of the art. So the blue line here is the exact numerical evaluation of the spectrum. So this is numerical calculation, which has been done recently, a few years ago. Now, if you do the harmonic oscillator approximation, so the harmonic oscillator approximation is the one that neglects the Coulomb log and that leads to this 1/√omega behavior that we discussed earlier. Well, it's the green curve here. Well, it does reasonably well in the regime, the LPM regime, all the way up to omega c is around here. But then above omega c, because it doesn't describe well the Hartz regime, it fails, right? So it doesn't really work very well. Now, if you do the opacity expansion, which is here denoted by GLV, this GLV spectrum, it assumes a single scattering. If you assume a single scattering, look what happens. Well, it does well at high frequencies. You see it here, this is the dotted line here. It does well at high frequencies. This is what I said. So high frequencies is dominated by a single scattering, okay? But at low frequencies, it fails. It overestimates the spectrum because it doesn't account for multiple scatterings that leads to the LPM suppression. So you need to account for the multiple scatterings to all orders to bring this down to this here. So neither, approximations do well everywhere, right? So you need to do better, right? Or you can stitch the two distributions, but this is not accurate enough. Now, what you can do, and this is what has been done also recently, is to expand, instead of expanding in powers of the scattering centers, you expand around the harmonic oscillator in powers of the Coulomb log. This is a new technology. And using that, you can solve analytically, first order, second order. And to NLO, you get this red curve here. And you see the red curve is doing very well and compares very well with the still an approximation, but the systematic approximation that leads to the pretty good description. So this is the state-of-the-art calculation of the medium-induced spectrum. So as a final remark, if I'm allowed to use one last minute, okay. Final remark is, all right, so what's the general picture we have now of jet quenching? So there are theorists among you who wants to do calculations in jet quenching, so what is the technology? Well, the technology is now using a refactorization of the jet function. Right? So I introduced the jet function in yesterday's lecture. for the physics in vacuum. Now, you need to factorize different regions of phase space. First one is the region where now you have collinear hard modes that are very hard but collinear, produced as in vacuum. And they obey Diglab evolution equations, right? And this happens around scales which are very hard, Q of the order PTR, we discussed yesterday. So these guys, they are very hard and they proceed through, they go through the medium without suffering much deflections. These are the ones that are, undergo an iconal interaction with the medium. But they are produced very early, before the medium is formed. They obey Diglab equation. And these hard collinear modes, they go through the plasma, right? And the interaction with the plasma, all of the soft physics is encoded in the Wilson lines that account for the soft radiation that leads to either momentum transfer in the medium directly or gluon radiation. So this is the factorization. So now the jet function takes this form. It's a sum over the number of hard modes in the jet. Okay, and then you have a convolution of these matching coefficients, which can be computed order by order in perturbation theory. There's, of course, dependence on the certain factorization scale times Wilson line soft functions or Wilson line operators, which describe the physics at the medium scale, which are just correlators of Wilson lines. So this is the field theoretical formula for jet observable for inclusive jets, which you can use now to compute order by order or resum to all orders certain type of diagrams. All right, so this is it. This is my last slide. Hopefully, this was not too complicated at this level, but I wanted to cover all aspects, whether it's in terms of really parametric discussions, really basics, and also some of the technology that is used that you can, if you are interested, use it yourself and really actually do state-of-the-art calculations. Thank you. Now, if you have any questions.
Thank you.
Slide 26, you showed the, yeah, so this is just for the induced radiation, right? So what is that gray area?
So the gray area is the region where the frequency is of the order of the temperature or below, temperature of the plasma, 1 GeV. And this analytic approach breaks down there at the temperature scale.
Okay.
Right? But this region, in fact, does not really affect much because we have infrared safety. So the observable, not the spectrum, but the observable is infrared safe. When you, because you have cancellation between the real and virtual, this region does not really affect much the observable. It's really very soft. So you are really at the edge of the phase space.
And there are like two curves that goes into the gray area, but like two curves that doesn't go into the gray area.
Yes. So this curve here, the curve, the GLV doesn't really care about it. So it can, of course, analytically you can just extend it all the way down, right? For the green and the red, which are based on the same approximation, which is the expansion around the harmonic oscillator, we have a log in the problem. And the log, of course, at some point the log turns negative. Right, when the frequency is too small, right? It turns negative. This is where it breaks down. So you need to go beyond the log, this log approximation. Which let me go back in here. See, so I am approximating this integral by x squared log, which assumes that x perp here transverse is much smaller than the biomass versus the biomass, and it breaks down when around the temperature scale.
And like this is as a function of omega, like can I also calculate a function of like the angle with respect to the initial hot jet?
You could, yes, of course. You can go beyond that, and this is integrated over transverse momentum. But you can also calculate the spectrum. It's more of course involved. You can compute the fully differential spectrum as a function of angle and omega using the same technology, and then yes. You can do that.
Thank you.
So is the centrality
Dependence of the modification factor encoded in Q hat.
Yeah, right. So this is to a first approximation, this is how the centrality dependence is going to be accounted for. By assuming a certain profile for Q hat that encodes the centrality dependence, the time dependence, and so on and so forth. You could have other transport coefficients in the problem. You could imagine basically having other dependencies on the geometry and through other, but this is like the simplest, the leading order type of approaches where only Q hat encodes this physics. So when
in hydrodynamics, when people try to account for the energy deposit of jets into the medium, they usually do like a dimensional analysis, have like powers in like the length, the system size or the energy loss. They parameterize the energy loss. You know, what would you say is the validity of that, and to what extent, where would that break down?
yeah, so the coupling of a jet with say hydrodynamics is tricky, right? So this is not so it's model dependent where you couple it because you have a singularity. The jet is a singularity, right? You need to assume a certain, and hydrodynamics is physics of long wavelengths, right? You can't just start with something that is a source that is point-like and you just feed it into the hydro. So you need some. So the coupling is so all of this. I mean, of course, you can couple this physics of jet evolution with hydro. By once you hit a certain scale, let's say the temperature scale, then you say, well, I'm going to feed it to hydro. This is what people do usually. So they feed to follow then the dissipation of energy into the plasma. But then it's the sensitivity of your calculation to this physics is really depends on the observable. If you're looking at bulk observables, then of course if you look at the soft physics, then you're going to be sensitive to this. But if you are interested in the hard physics, suppose you look at the jet spectrum, you shouldn't be sensitive too much to this physics. So the hydrodynamics in the context of jet quenching is really the details of what happened there become important only if you're interested in the soft components of the jet, but not so much when you are looking at high PT particles. So again, at high PT, you're mostly sensitive to Q hat, and Q hat can also be described by you could have a hydro calculations that the profile, by the way, of Q hat is sometimes given by hydrodynamics. Give you the profile of pure plasma.
Is that where the different like hybrid model and all the other stuff, when you try to implement the hydro, when people start to calculate the what's it called? I only can think of is the bake.
Yeah,
Make it
that's how they do exactly.
Okay.
Yeah. So this is some kind of back reaction. So you kind of inject some energy to the plasma, and you see how the plasma responds to this the passage of the jet. But this is soft physics. You have to look at the soft components.
All right, thank you.
Why my question is the following: why you have, for example, in GLB solution, very close to next to leading order when the frequencies approach to 1. And then if you have some mixed solution, including leading order, so you may have two areas, the solution. That is so similar to next to leading order.
So the GLV.
Yeah, you have very close solution to NLO solution when the frequency goes to 1.
Exactly, yeah. So GLV is a very good description of the physics in high frequency. Okay, so what the NLO is doing is in fact accounting for this tail. So the NLO is the next order in the harmonic oscillator, so it accounts for the Coulomb log, which is encoded in the GLV.
Okay.
So the GLV has the full spectrum here, but at leading order. So you just expand to leading order this guy, right? But it has the full potential with x squared and the log. Okay, so the log is responsible for this tail at high ohms.
So almost similar.
It's the same. It should be the same, right? So but if you neglect the log, you're going to miss that high. So the NLO is the next order accounts for the log, and that's why the GLV and the NLO are similar, because they are so at very high frequencies the NLO just should match the this GLV spectrum.
And when you go to zero, the
So
the leading order is similar to leading order in LO. The range is close to.
yeah, so now the green, okay, so now the green,
You can split the solution.
you can
That's
split.
my thing.
It's exactly the idea. So the idea is that you have a good description at high frequencies given by the GLV. Then at low frequencies, you have a good description given by the harmonic oscillation.
Yeah.
So what you can do is just stitch them together. You can just interpolate. You say, well, I'm going to use this one in this regime and the other
And
one.
the normal.
But it's not satisfactory, right? Because you say, well, I can do that, of course. But what you want, you're going to lose somehow. You don't know how you're going to stitch them perfectly. It's not systematic and so on. This approach, which is called the improved opacity expansion, does it systematically for you. So you can even compute really you see it here. I mean, it does a pretty good job everywhere, even in the, there's no stitching going on there. So it's more systematic. It's more, let's say, elegant approach to the problem rather than just stitching. But you're right. I mean, this is the idea. The core idea is to be able to
Yes.
kind of interpolate.
Let's thank is one again. Half an hour break. Come back 15 to 11. How much?